Hello friends. So, we have seen some of the methods of computing eigenvalues and eigenvectors where we targeted one eigenpair at a time, and then having computed one eigenpair at a time we converge to the next eigenpair by using some sort of orthogonality or purification technique or even shifting procedure, and we could compute the other eigenvectors, the next eigenvectors in the spectrum. So, now we look at some of the algorithms which are used for more large scale eigenvalue problem, and first one very powerful and very popular technique for large scale solution of eigenvalue problem is what we call as QR iterations. In numerical analysis or numerical techniques books, it is often referred to as HQRI, or H standing for Householder transformation. So, and QR refers to the factorization. So, using Householder transformation matrix, the reflection matrix, we convert this matrix A into a factor of orthogonal matrix Q and a right triangular matrix. So, R, because this is a matrix on the right of the matrix Q, and it is it has a triangular structure. So, matrix Q is actually generated from A such that this will reduce this entire system reduces it to upper triangular matrix. So, A is converted to upper triangular form. So, a matrix can be transformed into upper triangular form by a series of Householder transformation. So, it is very efficient to convert matrix a given matrix to upper triangular matrix by using Householder transformation, and that accumulation of the transformation, that sequential accumulation, that is what is we call as the transformation matrix that is related to Q. So, R 0 is upper triangular and Q 0 is an orthonormal matrix, and this orthonormal matrix is related to the Householder transformation gradually. So, essentially what is done is A, if I multiply this Householder transformation P 1, then I will get this matrix and 0 0 0 0 here, and then of course, there are other rows that are there. So, it can be done like this, and then once I do P 2 transpose, it will target this matrix and there will be elements here, and then there will be zeros all along. So, these matrices, the product of these, this is what refers to, if I look at it, then Q 0 transpose A is equal to R, because this is what is going to be converted to upper triangular matrix. And if I multiply Q 0 transpose is of course orthogonal matrix. So, A is given as Q 0 R 0, let us say A 0, right. So, this is what the entire factorization is. A can be defined as a orthogonal matrix Q 0 multiplied by right triangular matrix R 0. Now, if I define another matrix, let us say A 1, as I reverse the order, what happens? R 0 Q 0. Having computed QR factorization, I just interchange the order of matrix multiplication and define a new matrix. So, what is this matrix? This matrix I can write this as Q 0 Q 0 transpose R 0 Q 0, because this is a orthogonal matrix. So, Q0 transpose is of course identity matrix. So, when I do this, then this is actually orthogonal transform, and sorry, I would so I define this Q transpose Q and R 0 Q. Now, Q 0 R 0, what is Q 0 R 0? Q 0 R 0 is just A 0. So, this essentially this by reversing the order of multiplication, what I am eventually doing is implementing a similarity orthogonal similarity transform of matrix A. A very efficient technique. So, this similarity transform would require multiplication. Ideally, if I do implement it, then it will require multiplication of 3 n by n matrices, and here I am doing the same operation by just multiplying 2 matrices, a considerable saving in numerical effort. So, we define new matrix by reversing the order of multiplication. So, A 0 is the factorization by series of Householder transformation, we get Q 0 R 0, A 0 is equal to Q 0 R 0, that is the factorization, and then I define new matrix A 1 by just reversing the order of multiplication R 0 Q 0, and multiplication in reverse order is effectively performing an orthogonal similarity transform by virtue of identity that we have, and the sequence we can keep on doing this repeatedly, and we can do this A I is equal to Q I R I, and this new matrix will lead to R I multiplied by Q I by interchanging the order, and so on. The matrix factorization and reversed operation, reverse multiplication can be continued until A is reduced, until this matrix A that we have is reduced to upper triangular form, completely upper triangular form, and that will have, that is called Schur form with eigenvalues on the diagonal of the matrix. And once we have the eigenvalues, then it can be, we can go back to inverse iteration with shift parameter to compute a refined eigenvalue and the corresponding eigenvector, and generally one iteration is good enough to compute the corresponding eigenvalues and eigenvectors. So, in this case by the QR iterations we can actually converge to the eigenvalues on the diagonal of the matrix. So, this diagonal matrix that we generate. So, in practice, that is the theory that for QR iteration. In practice, we actually first consider the Householder transformation to convert matrix A into upper Hessenberg form. So, upper Hessenberg form is like upper triangular structure with one subdiagonal, and rest of it is all 0. So, this is all 0. So, this structure is what is known as upper Hessenberg form. So, we convert the matrix, instead of converting into right triangle upper triangular straight away from using Householder transformation, we just use it for converting it to upper Hessenberg form. Now, why do we do this upper Hessenberg form? We do this because not all eigenvalues are guaranteed to be real in general case. So, if they are complex eigenvalues in some cases, then those complex eigenvalues must occur in pair, and those complex eigenvalues would appear, I mean in this real matrix they would occur as 2 by 2 sub blocks on this upper Hessenberg form. So, this upper Hessenberg form is capable to also represent the possibility of complex eigenvalues being there in the matrix. So, of course, for symmetric matrices they are no we do not have complex eigenvalues, but for a general unsymmetric real matrix we can have eigenvalues that are complex, and for that purpose instead of looking at upper triangular factor we look at matrix transformation, Householder transformation to reduce it to upper Hessenberg form. And when we do this for QR iteration subsequently, if there are any complex eigenvalues they would appear as 2 by 2 sub blocks diagonals on this upper Hessenberg form, and the eigenvalues would be obtained from solving the 2 by 2 eigenvalue problem, and the complex conjugate eigenvalues can be recovered from there. So, subsequently we try to, once we have this upper Hessenberg form, then there is only theoretically there is only one off diagonal term in each column that needs to be eliminated. So, the QR factorization is achieved by using Given's rotation, subsequent Given's rotation. So, we accumulate Given's rotations and convert this H upper Hessenberg form into a QR factorization and then reverse the order to get the next upper Hessenberg form. Now, convergence can be accelerated by introducing a shift to the Hessenberg form before factorization. So, instead of H 0 we can factorize H 0 minus mu I, where mu is the estimate of an eigenvalue. Now, Hessenberg matrix for the next iteration is obtained by reversing the order of multiplication and by undoing the shift in the that was implemented in the first iteration. And then once we have this H 1, then again Q 0 R 0 will again be computed by having new shift parameter depending on what is the new H 1. So, this shift parameter is generally taken as the n element of Hessenberg matrix, and it is a generally good shift parameter in view of Gershgorin theorem, because there is only one off diagonal term, and so there is an eigenvalue which lies in between H n and plus or minus the off diagonal term. So, H n is generally a good estimate of an eigenvalue, and this shift parameter, it is a good choice for shift parameter. But of course, this is only for when eigenvalue is real. For complex eigenvalue the procedure becomes little more complex, in the sense that we now need to look at 2 by 2 sub diagonal 2 by 2 block diagonal elements and implement that in the shift parameter. So, that procedure is a little bit involved, but that can also be taken care of in numerical operations. So, this is a workhorse, and householder QR iterations, they generally work very well, and they need to be followed up with one cycle of inverse iteration with shift parameter to compute a really very good very accurate eigenvalue and corresponding eigenvector. So, this QR iteration they will provide us with the eigenvalues of good approximation of the eigenvalues along the diagonal of the triangular matrix that we eventually get by repeated iterations. Now, we look at what is known as the subspace iterations. Subspace iterations is an extension of power iteration. It is also referred to as simultaneous iteration, and just as in power iteration or inverse iteration we dealt with one vector, one trial vector. In subspace iteration we actually use a set of independent vectors for iterations. So, instead of just one vector in power iterations direct or inverse, we choose a set of p number of independent vectors in real number space and then perform incomplete QR factorization. So, x 0 there are p number of vectors in this x 0 matrix. So, it is n by p matrix. So, this n by p matrix we can perform incomplete QR factorization in the sense that this is q 0 is of course n by n and R 0 is n by p matrix. So, R 0 will be upper triangular p by p and rest of the rows n minus p rows, they are all null matrix, entirely null matrix. So, q 0 that contains first p columns, I mean q hat contains the first p columns of the orthogonal q matrix and R hat is p by p, that is upper triangular matrix, upper triangular I mean rest of the things n minus p rows are all zeros. So, q 0 is the orthogonal n by n matrix and q hat is first p columns of this orthogonal matrix. So, eventually we perform these iterations. So, x I is given as this decomposition q I r I and then we define new set of trial vectors x I plus 1 next iteration as matrix A operating on this incomplete orthogonal matrix q I hat. And once I obtain this new set of eigen trial vectors x I plus 1, I again decompose them into factorization q I plus 1 multiplied by r I plus 1 hat and again go back to the system and diagonal elements of r I plus 1 hat, they converge to eigenvalues as I tends to infinity. As iterations progress, the diagonal elements of this triangular matrix R, they would converge to the eigenvalues. And once we have the eigenvalues, then again the one cycle of inverse iteration will lead to a very accurate eigenvalue and corresponding eigenvector, or we can just substitute in this eigenvalue into the governing eigenvalue problem statement and compute the corresponding eigenvector directly. So, convergence depends on closeness of vectors x 0 to the lower eigenvectors of A. So, this choice of vectors that we have, if they are in some way representative of the lower end or the eigenvectors corresponding to smaller eigenvalues of matrix A, then the convergence is going to be very, very rapid. So, the basic steps, I mean for generalized eigenvalue problem, what we discussed here is for the standard eigenvalue problem A x is equal to lambda x. For generalized eigenvalue problem, things become little more involved in the sense that there are two matrices and the trial vectors need to be computed as a solution first. So, for starting with x k trial vector, we find what is b times x k and then find what is the new trial vector x k plus 1 hat going to be by solution of this system of equations. And once we find this x hat k plus 1, we compute its incomplete QR factorization, and this incomplete QR factorization we impose similarity transform on A. So, q hat k 1 k plus 1 transpose A q hat k plus 1 is equal to A k plus 1, and similarly q hat k plus 1 transpose B q hat k plus 1 is defined as b k plus 1. Now, you look at it, these are all smaller size, I mean k plus a k plus 1 and b k plus 1, they are in general smaller in size than a and b, because these are incomplete factorization. So, while a and b are matrices of size n by n, a k plus 1 and b k plus 1 would be matrices of size p by p, which is generally very small compared to n by n. And then this small system of eigenvalues, problem is solved by suitable technique, whichever technique we may adopt. So, this smaller eigenvalue problem, now this small eigenvalue problem, it is what we need to appreciate, that we are looking at scaling down by several orders of magnitude, while it is common in case of typical finite element problem that a and b would be of the order of several millions in the size, while these matrices a k plus 1 and b k plus 1, these are we are referring to only of size a few hundred by 100. So, that is a tremendous saving or reduction in problem size, and this eigenvalue problem, this is the reduced order eigenvalue problem which can be solved, and once we can solve this problem, then we find new set of eigenvectors as q hat times the eigenvectors of this smaller eigenvalue problem, right. And then again the entire cycle begins from this step again. So, again we multiply b with this x k plus 1, find out what is x hat k plus 1 by solution of simultaneous equation, and repeat this process again. So, reduced orders eigenvalue problem that we had been looking at, they can be solved either by generalized Jacobi method. We will discuss that generalized Jacobi, which is actually a series of Givens rotations, so that the matrix is nudged to diagonal form, or QZ iterations, again similar to QR iterations, but QR iterations refer to standard eigenvalue problem, QZ iterations refer to generalized eigenvalue problem, where we perform decompositions on both the matrices. So, alternatively the generalized form is reduced to a standard form, as we discussed earlier. Matrix B can be converted to Cholesky factorization LL transpose, and then the problem can be transformed into standard eigenvalue form, and then it can be solved by using QR iterations. The guidance of how many numbers that we need to take, the vectors, is given by a maximum of 2m or m plus 8, where m is the number of desired eigenvalues. So, as I said, the size, the matrix A and B can be of several millions of degrees of freedom, and accordingly there are going to be millions of eigenvalues, but not all these eigenvalues are required. So, we can work with very few eigenvalues and maybe only a few hundred. So, those 100 eigenvalues, so if I need 100 eigenvalues, then the number of the columns independent vectors that I need to generate for these use in subspace iteration is only going to be twice m. So, 200 vectors that I need for completing the problem, and the size of the problem that I will need to solve eigenvalue problem would only be 200 by 200 instead of several millions. So, that is how the subspace iterations are arranged, and then Jacobi iterations is as I said, it is successive orthogonal similarity transform by using Givens rotation to annihilate the largest off diagonal element, and that is what we do, and we do it from both sides until the matrix A converges to the diagonal matrix, which are the eigenvalues. And interesting part is accumulation of these product matrices, orthogonal matrices, then converges to the eigenvectors, and that in a sense is the Jacobi iteration. So, it is essentially a sequence of Givens rotations, and we can find out what is the iteration and how to arrange for that. And for generalized eigenvalue problem, there can be generalized Jacobi transformation, again using similar rotation matrices on both the terms, both the matrices A and B, and such that they are progressively nudged towards diagonal both of the matrices, and eigenvalues are obtained as the ratios of the diagonal corresponding diagonal elements, and that in a sense is Jacobi iteration. And the problem is Jacobi iterations, they will provide us complete eigenspectrum as on in one go. So, it is all or none. So, either we get the complete eigenvalues and eigenvectors or we do not get any. So, that is the problem, and for this is the similar arrangement for Givens rotation, but for generalized eigenvalue problem there is a standard algorithm that can be arranged, and coefficient rotation matrices or orthogonal transformation matrices can be defined as a modification of the identity matrix. You can see that there are two elements which differentiate, which make this rotation matrix different from the identity matrix, and these coefficients are evaluated from the solution of these equations. So, eventually this is what we have for definite positive definite B. The solution can be obtained for these nonlinear equations, and similarly QZ iterations, they are similarity transforms, two sided similarity transforms similar to QR iterations, but these are applicable to generalized eigenvalue problem. So, this advantage is these QZ iterations, they are robust numerically even if matrix B is near singular. All other algorithms that we have discussed for generalized eigenvalue problem, Jacobi rotations etc., they work only when matrix B is positive definite, but QZ iterations would work even if the matrix B is nearly singular or not very well conditioned. So, simultaneous reduction of A and B to upper triangular form, and that is what we call as generalized Schur form, and then the eigenvalues are obtained from the ratio of diagonal terms of the respective diagonal elements, and once we have these eigenvalues, then the corresponding inverse iteration can be computed, and associated eigenvectors can be generated. So, with that we stop the discussion, and Lanczos iterations are again related to Krylov subspace that we had encountered in the discussion of conjugate gradient method, and they are essentially related to converting it to tridiagonal form and then using the similar orthogonal transformation, and then it begins to converge from both ends. We get the eigenvalues from the lower end of the spectrum as well as from the higher end of the spectrum, and both extreme eigenvalues can be obtained gradually, and then it moves to the center. So, in some applications Lanczos iterations are quite useful, but for most of the cases we will find that QR iterations and subspace iterations, they more than serve the needs of the computation that we need. So, with that we end our discussion on eigenvalue problem. Of course, this is a very vast subject, and I just skimmed at the surface of this, and hopefully that should allow you to explore this particular subject in more detail on your own. In next lecture we start with integration of equations of motion in time. Thank you.